Hello friends, welcome to another video from CFIEL Academy where we learn together from each other. So today's topic is Dijkstra's algorithm, which is basically an algorithm to find shortest path to all the vertices in a graph from a given source vertex. So let's get started. So shortest path from a source node. So shortest path from a source node is basically a set of edges in a graph in such a way that the total weight of the edges or the sum of the weight of the edges to that particular destination is minimized. So let's say we have a source vertex here and we have another destination vertex here, and there are many other vertices in between. So our goal is to find a path that is shortest. There might be multiple paths from S to D, but our goal is to find the shortest path or the path that costs us less. And finally, similarly, we have to find the shortest path to all other vertices from S. That is our goal, and that's what Dijkstra's algorithm is used for. So Dijkstra's algorithm is again a greedy algorithm, so which means at every step it computes some value and then updates it based on any new information that it has gathered from the new vertices. So it works for directed as well as undirected graphs, and the basic idea is it has a distance vector, which means basically a vector containing distance to all the given vertices of the graph, and in every step it will explore newer vertices or new vertices and then keep updating those distances in the distance vector. And finally, when it has explored all the vertices and edges, the final distance vector that we'll have will be the final answer or the final value of shortest path from the given source node. So little bit of history about Dijkstra's algorithm. So it was invented by Dutch scientist Edzer W. Dijkstra. That's where the name Dijkstra comes from. It was done in 1956. So let's see how it works. Intuitively, what it does is it will have a distance vector, which means it will have a matrix of distance and its value. So in distance we will have all the given vertices v1, v2, v3, and initially it will update those distances as infinity, which means since those vertices have not been yet explored, I just initialize them to a very high value so that the next time when I find it, I keep updating it. So in the next step, what it does is, or in the subsequent steps, from the given source vertex, it tries to explore the newer vertices, the other vertices. Let's say v1 here, we have v2 here, and we have v4 here. So as it explores new vertices, which means in the first step it will explore v1, it will update the distance based on the current distance vector and what it has found so far. So which means if it sees that the current distance from of v1 is, let's say, x, so it will add x to the previous distance of s, which means it's 0. So 0 plus x is x, and then since x is less than infinitely, it will update v1 to x. Similarly, it explores the other vertices and updates the distance vectors, and finally at the end, the final distance vector will contain the size of all shortest paths from the given source vertex. So let's take an example and see how it works. So here is a graph given to us which has 6 vertices, S, A, B, C, D and E, and we have weights on each of the edges, and we are given a source vertex S and our goal is to find the shortest distance from source to all the other vertices. So first step, initialization. What is the initialization? We will initialize the distance to all vertices, which means distance of A will be infinity, distance of B will be infinity, distance of C, D, E all will be infinity, because I haven't explored them yet. And I'll update the distance from S to S is 0 because we are already at the source vertex. So this is how our distance vector looks like. So we have S2, which means distance of S is 0, whereas all others are infinity. So as we have just initialized, now let's go ahead and apply the algorithm step by step. So first step is to explore the edges and vertices that are near or that are adjacent to the current source vertex. Now what are the vertices adjacent? Vertices adjacent are A and B, which means we'll pick edges SA as well as SB. Now we have found edges SA and SB, and we have found two vertices in fact, so we need to update the distances of both the vertices, distance of A, distance of B. So distance of A is currently infinity, distance of B is also infinity, but then we have found a path, or we have found a new edge SA, which is of weight 1. So what will be the distance of SA? So distance of SA is just 1 because we are able to reach A in just one step. Similarly, distance of B will be 5 because we are able to reach B in 5. So in short, what it means is distance of vertex A is whatever the previous value was, which means infinity, and whatever the new path that I have deciphered. We have to just find a minimum between both. Now the earlier distance of A was infinity, and the new path that we have discovered through S, that is ds plus SA, has weight 0 plus 1. So which means our new distance is now 1. Similarly, computing distance of B is just 5, and then we just go ahead and update the distance vectors of A and B in our distance vector. So this was iteration 1. Similarly, we have to start with a new iteration now, iteration 2. Now for iteration 2, let's pick vertex A, and we will find all the edges from A. So what are the edges from A? AB, AC and AD. So which means we are now touching 3 new vertices, B, C and D. In fact, we found B already, but then it's possible that the distance of B again gets updated based on the newer path that we have found. So let's go ahead and update the distance vectors of these 3 vertices, B, C and D. So first, distance of B. So what was the previous distance of B? Previous distance of B was 5. And now what would be the distance of B that we have found through A? So distance of B through A is nothing but distance of A and distance of A, which means 1, plus the edge AB, that is 1 plus 2, which is 3. So distance of A plus AB is 1 plus 2, which is 3. Now what was the earlier distance we had? Earlier distance was 5. So we notice that we have found a new path SAAB to reach B, which is just in 3. Hence our distance of B is now the new distance vector, or the new distance value of B is 3, which means we have found a newer path to B of just weight 3, which costs us just 3. Cool. Moving to distance vector of C, the distance of C. Now distance of C was earlier infinity, and through our path is 1, plus 2, which means 3. So we have updated it to 3. And distance of D would be 1 plus 1, which is 2. So this is a new distance. So notice our distance of B gets updated, whereas distance of C and D is now changed to 3 and 2. Alright, cool. So we have found some edges and vertices, but we still have some other edges and vertices which we have to cover. So next we'll go to iteration 3 and let's pick vertex B. And what are the edges from vertex B? So there is only one edge BD from which is of weight 2. So which means we have to only update one vertex here, which is D, based on the new edge BD. And let's see if we find a smaller path to D. So distance of D was earlier 2, as we can see here, and distance of D through B is DB plus BD, which means 3 plus 2, that gives us 5. But notice earlier we have already found the shortest path to D of weight 2 of cost 2. So there is no need to update. We will keep the same path and we'll ignore the new path that we have deciphered. That's why we take the minimum of 2, which was the original path, and the new path that we have found, and we keep it as 2. So we don't update the node D, or we don't update the shortest path of D anymore. So we are done with vertex D. Next iteration, now we will take vertex C and then update the paths of the vertices that are near to C. So iteration 4, vertex C, we have two edges, CD and DE, which means we need to update the distance vector of D as well as E. So distance vector of D, which was earlier 2, and we now, since we have found vertex C, we'll use the vertex CD to find a new path, which means the distance of C plus the edge CD, which gives us 3 plus 3, which is 6. So the newer path that we have found through C is of weight 6, but then our earlier weight was 2, which was much smaller, so we no need to update vertex D. Same principle will apply to vertex DE, but remember the distance of E was infinity, so which means there was no path earlier, and in fact we have found a new path to E from C, which is 3 DC plus CE. So 3 plus 1, in fact 3 plus 1 gives us 4. So we update the distance vector of E as 4 in the next step. So this is what we do. We update the distance of E, whereas there is no need to update the distance of D. Cool. So we are done with vertex C. Now next move to the next iteration, in which case we pick the next vertex, which is D. So what are the new edges? There is only one edge, DE, which is of weight 2, and the new vertex that we have is E. So we have to update the vertex distance of vertex E based on the new path we have deciphered. So the new path we have deciphered is DE, and the weight of D was, the distance of D was 2, new path is 2, so we have 2 plus 2, which is 4. And what was the earlier distance of E, shortest distance, which was also 4. So which means we have just figured out another path of 4. So in this case we may update or we may not update, because the distance still does not change, so the distance remains the same. So if you notice, we are done with all the edges and we have found all the vertices now, and hence the distance vector which we have is the final answer. So this means the minimum the shortest path from vertex S to A has size 1, S to B has size 3, and so on. From S to E has size 4, which is our final answer. Cool. So finally we are done with the algorithm. Thanks for being patient with me, and I hope I tried to explain it clearly. So definitely, if you have any more questions or if any steps was confusing, feel free to comment and I'll definitely reply back to you. So before we end, here is an exercise for you. Take the same old graph which we have been using, but now rather than using the source vertex as S, let's take the source vertex as E and repeat the same process. Find the shortest path of all the other vertex from E. Now this could be a tricky question, notice, because the graph is directed, but nevertheless I would recommend you to try your best and then post comments on the video if you are able to do it or if you are not able to proceed it. And here is something to think. Now we have another problem called as all pair shortest path, which is to find shortest path from every vertex to the every other vertex, which means you pick any pair of vertex and we should be able to give the shortest path or the shortest path size. So the question is, can we use Dijkstra's algorithm over and over again repeatedly to find all pair shortest path in a graph? So keep thinking as we end this video here, and I thank you again for watching the video, and make sure you watch other videos on my channel and subscribe the channel if you like it from your videos. Thanks friends.